So, welcome to this new AJS. Today, AJS, we have us present. He is Davide Oberto. He is a postdoc here in SISSA. Thank you very much for your invitation. Thank you very much for having added another AJS which covers fluid dynamics topics, because this year there were a few. So, today's talk is entitled Closing Runs Through Machine Learning, Enforcing Physical Properties and Application to Model Organization. So, okay. Davide, the stage is yours.
Okay. Yeah, just why are you're not working? So first of all, thanks Nicola for the introduction. I'm facing issues because why not? What do you see now? It's cut.
If you can move the bar.
The bottom is cut.
Maybe for tips. Or
Oops. No. Just let me try. Okay. Okay. Sorry for the inconvenience. Okay, so
the same.
Sorry?
Che non è
perché qua, ok, scusate. Non è questo devo fare, questo. Proviamo a fare così, forse adesso. No, okay, no. You see, as soon as I share, I can.
Okay, then
wait, we don't care about videos, and I can.
Well, maybe you can see the video later.
Yeah.
Example between the presentations.
One more minute. I waited for you now. Let's do this way and. Are you able to see my screen, William? Okay. So we can start. So model order deduction. So here we have the contents. I'm going to give you some motivations about turbulence, basically. Many already know this stuff, but it's useful to talk a little bit about it. And then I'm going to present the main core of my PhD work, that was the definition of the vector basis neural network framework to closed runs equations. And then we will see how we can naturally couple this framework with model order deduction. So here I had some videos, but the pictures are fine. Turbulent flows are fascinating from a physical perspective, but also are of paramount importance in engineering applications. And they are characterized by high Reynolds number, meaning that the convective nature of the flow is more important than the diffusive one. So here on the left, you can see a simulation from Nicola about an academic case. So more about the physical perspective of turbulence, and on the right you can see an application on aerospace engineering with a network profile. And you can immediately see that turbulence is a very multiscale phenomenon, in the sense that you have big scales of vortex that are very big, comparable to, for example, the length of the airport, but you also have very small vortices, and the same is for the time scales. You have high frequencies and low frequencies in your turbulent flows. And the issue is that all the scales are important. Turbulent flows are can be described by this energy cascade process, in the sense that you have your main flow that for instabilities generates some big vortices, and these vortices are unstable themselves, so they split into smaller vortices, and they are unstable, and they split and split and split, and so on and so forth, until they have a very small scale that is usually referred as Kolmogorov scale, where each vortex has not energy enough to split again, and it's dissipated by the viscosity of your fluid. So all this process is important from a physical standpoint, and you really need in your simulation to keep track of this Kolmogorov scale in order to describe in a good way your turbulent flow. Otherwise, the numerical dissipation of your steam is dominant with respect to the physical dissipation. And so the problem here, I'm showing the Navier-Stokes equations, where U is the velocity field, P is the pressure field. And Navier-Stokes equations describe perfectly the turbulent flows. It's not a problem of model. The problem is that if you want to discretize Navier-Stokes equation by the so-called DNS approach, you need to have a discretization that is small enough to describe the Kolmogorov scale. And from turbulence theory, we have that the Kolmogorov scale depends on the Reynolds number with this value. And so in engineering applications, you can have easily a Reynolds number that is of the order of 10 to the 6, even more. And for a Reynolds number of 10 to the 6, you would require a space discretization of the order of 10 to the minus 8. This for each dimension of your problem. So in a 3D setting, you would require 10 to the 24 discretization points. It is completely unaffordable from a computational perspective. And so the idea is that we have some DNS results in literature, but for very basic geometries with moderate Reynolds number and using massive computational resources. And so it's basically used as a research tool to try to understand physics and not for engineering applications. One of the approaches to overcome this issue is to change the equations and work in a different setting, and to do so and by applying this Reynolds operator to the Navier-Stokes equation, one obtains the so-called Reynolds-Averaged Navier-Stokes equation. So pictorially, the idea is really this one: you have your fields and you split it into two parts. And once you apply this Reynolds operator and you compute some computations, you end up with these equations, supposing that the average is steady on time. And here I omitted the bar over U and P, but you have to think of this quantity as the Reynolds average for the means. And you see that the equations are very close to the Navier-Stokes equations, except for this additional red term, that is the divergence of a symmetric second-order tensor called the Reynolds Stress Tensor. And you can see that this tensor is associated to the covariance of the fluctuating parts. And you can think of this red term as the effect of the turbulence on the average fields, because it's the additional term you add to the previous Navier-Stokes equations. And the issue is that now you have in 3D four equations, one for the momentum balance, the three for the momentum, but you have also 6 additional unknowns that are the components of this Reynolds stress tensor that is not known. And so there is a huge literature that has 50 years about trying to close these models by obtaining this Reynolds stress tensor as function of average fields by adding basically additional partial differential equation to your model and close the system. Here I'm showing just two class of approaches of these classic Grant closures. The first one are the so-called eddy viscosity models, and they are based on the analogy I told you. Turbulence at the end takes energy from the average fields, and at the end of the energy cascade, the energy is dissipated by the Kolmogorov scale. So the idea is, let's write the effect of the turbulence as an additional viscosity that is called turbulent viscosity. And the idea is to write this turbulent viscosity as function of some scalar fields, turbulent scalar fields. For example, K, that is the turbulent kinetic energy, epsilon is the dissipation rate of the turbulent kinetic energy, or omega is associated to the frequency of the dissipation of the turbulent kinetic energy. And the idea that here now the unknowns are either K and epsilon, or K and omega, C nu is a constant. And so you need to write two partial component of the Reynolds Stress Tensor. It's a symmetric tensor, so you have 6 independent components, and you need to write an additional components for this epsilon, and so you have 7 additional partial differential equations, but they are not closed, and so you need to make some approximation of this additional partial differential equation to close your system. And once you have tau, basically, you can solve this momentum equation, and you solve explicitly as source term this term. Of course, the former approach is less expensive because you solve only two additional partial differential equation, and computationally is more robust because you are adding viscosity to your system, and so it's easier to obtain simulations that converge. While for the Reynolds stress transport model, the other one, the simulations are more expensive because you solve more partial differential equation, and in general, it's less robust because you treat this term as a source term. On the other hand, usually on the left approach is less accurate, and the right one is more accurate. But as I told you, you saw RAS closures are usually heuristically driven. You make a lot of assumptions to being able to obtain a closed system, and these assumptions usually hold for some typology of flows, but not for others, so they are far from being universal. And as an example here, I'm showing the so-called flow in a square duct. You have this duct with 4 walls, and you have the main velocity component here along X. And you can observe from the experimentally that you have some counterclockwise secondary motion that is occurring near the corners on the square sections. Here you can see the magnitude, so you have some flow near the corners. And if you look at the intensity of this secondary motion, here you can observe the DNS results. All linear eddy viscosity are unable to predict it, so they give you 0 y and zeta components of the velocity field, while a Reynolds stress transport model drastically overpredicts it. So the recent idea was, thanks to HPC facilities, now we are starting having some DNS data available. And because of the increasing interest in scientific machine learning in general, why not trying to use DNS data when available to try to train some machine learning algorithm to close these RAS equations? And the idea in this field is to try to define a machine learning algorithms that satisfy as many physical properties as possible, because on the one hand you obtain more accurate results, and the other one, when you try to extrapolate with your model, you have more robust results because we are enforcing these quantities. And so now I'm going to present a little bit my framework that I used during my PhD. And so the idea is, first of all, we want to define a model. We have to decide which field we want to predict. Usually in the RANS literature, models are written to obtain the Reynolds stress tensor, so tau, or its deviatoric part, so tau without its trace. And DNS datasets with less statistical errors. The idea is DNS is so computationally expensive that you don't wait. Maybe here the video can be useful. Just to give you an idea. Today is really a mess. So this is simulation from Nicolò. This flow is in average steady, but you can see that turbulence is unsteady by nature. So you can see that you have these small vortices that evolve in time, and when you obtain, you get the results from DNS, it's not the instantaneous field that you're looking for, but the average in time. So to get good results, you should run your simulation for a long time in order to obtain fields that are statistically at convergence in time. The problem is that these simulations are so expensive that the results you obtain are not very statistically at convergence because you can't afford to run your simulation for so long. So you have some statistical error. Okay. When you obtain your fields from DNS data, if you compute your Reynolds Stress Tensor, you see that you are averaging a covariance between two fields. And so this quantity converge much slower compared to fields that are first order statistics. And so you can obtain your Reynolds force vector by inverting this momentum equation, and you can compute, you see, by only applying this operator, averaging operator on U, or the gradient of U, or P, and you don't have these second order statistics, and so these fields are much more accurate when you are looking to DNS results. Once we have decided which field to predict, we have to decide how to predict it. And so the idea of, in general, machine learning, supervised machine learning, is to define some sort of map and approximate this map. Naive approach would be, for example, to take the average fields U, its gradient, the gradient of the pressure, and starting from these fields, infer the Reynolds force vector. But the issue is that this approach depends on the frame reference you choose. The idea is maybe I train my model on a frame reference, and a person want to use my model, but he ran the simulation by changing by taking a rotation of the frame reference. These are the fields that this person would insert in our model that are completely different from the one used for trainings, and the results you obtain are completely meaningless. So the idea, one approach would be to learn how to rotate. The problem is in 3D you would require to have 1,000 rotations, and so you have to increase your dataset by a factor of 1,000 and training using 1,000 more data. It is completely unfeasible. And this rotation learned is not up to machine precision, but you have some errors. So the idea is to try to define a way to impose this invariance a priori. How to do that? We're going to use some trick. First of all, we make a constitutive assumption. T tilde is our Reynolds force vector set dimensionless. And the idea is to say my vector field is some unknown function of some known tensor or vector or scalar fields. In particular, I'm saying here that is a function of all these fields are set dimensionless, and the symmetric part of the velocity gradient, that is a symmetric second order tensor, the antisymmetric part, that is a second order tensor, this vector field, this the gradient of the turbulent kinetic energy, and this custom designed scalar field. And these assumptions are not, let's say, obtained by computing by myself some computation. And by using these assumptions, we can use some representation theorems that guarantee that our vector field can be written as a linear combination of some vector basis that is known by means of these coefficients in the linear combination. And this linear combination is finite. The idea is that these vectors that I will call a vector basis are known. And for example, here I'm showing the first two. These coefficients of the linear combination, of course, are unknown, otherwise we would know everything. But they are unknown, but they are function of some known scalar fields. And so these scalar fields are usually referred as invariants, and we're going to see why. And they are non-scalar functions that depend on the second tensors and vectors we put here in the constitutive assumption. And so the idea now is if we knew the coefficients, we would know everything. So let's train a neural network that takes in input the known invariants, predict the coefficients, and once we have the coefficients, we can combine them with the known vector basis and build our Reynolds force vector. So the idea of this vector basis neural network framework is, given the invariants and the vector basis, we predict the coefficients and then build the Reynolds force vector. Why all this? Because we can satisfy some properties. First of all, the idea is these invariants are scalar fields, so they do not depend on the frame reference. And so if we rotate our system, the invariants will be exactly the same as before. And so when you feed them into the neural network, even if a person is the inputs of the model, so the person using my model is already rotating them in a correct way. And so the result is the correct rotated field. In addition, the invariants and the vector basis are Galilean invariant in the sense that they do not depend on the velocity. They depend only on the gradient, special gradient of the velocity. And so if you add a constant velocity, the gradient cancels out this constant velocity. And so you also guarantee Galilean invariance. That is an important property in run settings. Okay, so how to train practically our methodology? The idea is I have some DNS data from any simulations. So you can think of them as obtained from in a parameterized setting. And we want to decide a runs model that we want to improve. First of all, we run the run simulations by copying the setting of the DNS simulations we have, and we collect these invariants and vector basis for each computational cell of each simulation. Then, to have a one-to-one mapping between runs results and high-fidelity DNS data, we interpolate the DNS data on the runs machine, because usually, because DNS data must satisfy have a discretization scale that is of the Kolmogorov scale, they have much more data than the runs ones. Then you split your data into training and validation set, and you train your vector-based neural network by reducing this loss function that is basically trying to reduce the distance between the high-fidelity DNS dimensionless Reynolds force vector and the one we are reconstructing by linear combination with our approach. Okay, as you saw, the vector-based neural network is a very simple machine learning model. It's a feed-forward neural network where the number of inputs and the outputs depend on the constitutive assumption, because starting from that, you understand how many invariants you have and how many vector bases you have, so how many coefficients. In our setting, we found out that 8 hidden layers with 30 nodes each, and using a activation function was good enough. We used Adam, and the idea is we have very basic architecture with order of 10 to the 3 trainable ways. Once you have trained your model, how to make inference? You have a new simulation with an unseen parameter. You run your run simulation that you have decided to improve. You collect the invariants at the vector-based vectors, and you store k and epsilon for dimensionalization. You obtain your dimensionless Reynolds force vector with your trained vector-based neural network. You dimensionalize it, and you treat it as a source term. So you see, you have to first run the baseline run simulation, collect the data once the simulation has converged, and then rerun the simulation. So it's a little bit more expensive than running the starting a run simulation, but by starting the second run using as initial condition the condition you obtain from the baseline model, and because you're not solving the additional partial differential equation of your turbulence model, the second run is much faster than the first one. And in my experience, it is of the order of 20 or 50% the computational. So this term should be treated here as a source term. And so the idea is to split the contribution of this vector field into two terms, one that is a turbulent viscosity that you can treat implicitly, and one as the remaining part that you still have to treat as a source term. And so the idea is from DNS data, you can compute this turbulent viscosity by projection of the Reynolds Stress Tensor into the mean strain tensor. And you train two distinct neural networks, one that predicts a scalar field that is the turbulent viscosity, and one that is predicting the vector term. And so what you're solving for is this equation where now you have some viscosity added implicitly and the simulation runs much smoother. I want to show you some results. So again, with the square dot result, and as we saw, usually runs basically describe this secondary motion. And we decided to improve a linear edge viscosity that was one that was not predicting secondary motion at all. And we have DNS data available from literature at different Reynolds number. So you see the parametric setting I was talking about. So we train with several results at several Reynolds number and test in this setting. And this is what we have. So on the left, the DNS, on the right, the starting model, and in the middle, the secondary motion we are able to describe with this new turbulent viscosity-based vector basis neural network. Observe the difference of the refinement of the computational mesh you need to use when you are solving for DNS and for runs. Here, I'm using the same mesh for the VBNN simulation, the run simulation. So you see why it takes much less time to perform your simulation. And here, I'm showing also the contour lines of the main velocity component, so the x1. And the idea is if you are not able to describe the secondary motion, you're not able to describe the main motion because this secondary motion is moving along the diagonals, the high velocity field towards the corners. And so you obtain these square-like isocontours instead of these circle-like isocontours. So describing correctly the secondary motion is not a matter of being fancy, but it's also useful for the main motion. I want also to talk about another test case I worked with during my PhD, that is the flow around periodic hills. Here you have inlet, so the flow is entering here and going out here, and you have periodic boundary conditions. So the idea is you have infinite many hills. On the top and the bottom, you have walls, and you have this recirculation bubble that, of course, here near the first hill, basically the flow here reattach, and here you have back flow that is going backward, and it's alpha. The alpha is a geometrical parameter. It is that is associated to the steepness of these hills. So the smaller is alpha, the more steep is the hill. And we decided to improve this classic runs model, that is the K omega SSST1. And long story short, here you have the results. In this case, we did not use DNS data because they are so expensive to obtain. So we use a in-between model that is called delayed detached edge simulation. That is an in-between model between runs ALS, for people who know. And you can really observe that runs results over-predicts the horizontal velocity here and basically describe the recirculation. Now we have a working model, and I want to discuss a little bit of this joint work with Maria Strapsullo, former SISSA student, and my supervisor Stefano Berrone, on applying this methodology for model order reduction, also because this book is strongly model order reduction oriented. So the idea is, once we have our model, we are able to generate, we have a tool that is able to generate high fidelity simulation in the sense that have DNS-like accuracy at a limited computational cost. It is runs like computational cost. And as you observe, is very suited for parametric settings in the sense that you train this model in a specific flow configuration where there is some changing parameter that was the Reynolds ability to work with these high fidelity snapshots. And we decided to work a little bit with this flow in a square duct phenomenology. For this flow configuration, we have DNS data available at different Reynolds number, and this Reynolds number cover two distinct regimes for our flow. For Reynolds number that is smaller than 2000, the flow is transitional in the sense that it's not laminar anymore, but is still not completely turbulent. And on the other hand, when Reynolds number is higher than 2000, the flow is completely turbulent. And consequently, in literature, usually the approach is to train this data-driven model by choosing results only for Reynolds number greater than 2000. It makes sense because it's the region where Raster equations are meant to work. But we decided to challenge a little bit more our methodology, and so we decided to work with a wider range by starting by 1300s to 3500s. And we obtain, we have 13 simulations. And here I'm showing the intensity of the secondary motion with different Reynolds number, and you can really see the difference between these two regimes because basically the region where you have the maximum of the secondary motion are completely different into the two regimes. Here you have maximum, yes, on the diagonal, more closer to the center, but also in these particular regions, while you don't have these maxima here, and these maxima are much closer to the corners. So it's really difficult to, the phenomenology is varying a lot during in this parametric regime. And so we made a natural choice. We decided to train our VBNN neural networks by either taking all the results or taking in a first only the simulation with low Reynolds number or the results of the high Reynolds number. The idea is we train a global model and we compare it with two specialized models, one that focuses on the low Reynolds regime and one that focuses on the high Reynolds regime. And for each setting, we paid a lot of attention on the role of the regularization factor because we observed that is really important. And the idea is, and is quite expected, if you use Reynolds snapshots. So here you can see the mean square error for the turbulent viscosity and for the remaining part of the Reynolds force vector when you use the all model, so the one trained using all snapshots and the one using the two specializing into the two regions. And just before using the, now we have the snapshots generated by our model before using POD, for example. Let's check that the results are good. And so here I'm plotting here the profiles of the DNS. If you take this diagonal, I'm plotting the profiles of the intensity of the secondary motion across these diagonals. So you see you have these two maxima correspond to 1 and 2. And what I'm showing, and you can see that these maxima values are going towards the corners by increasing the Reynolds number. So we are going in this direction. And this is exactly what we are able to obtain with our NUTI VBNN model. You can see here the dots are the DNS maxima values, and you can see that both models are able to describe this maxima region is increasing. With the low-high model, it is much more accurate. Okay, I don't have to tell you what is the rationale behind the model order reduction because you are probably more expert than me. But the idea is now we are able to, we have these snapshots and we can try to extract the transformation matrix B using proper orthogonal decomposition to build up the model order reduction framework. The idea of model order reduction is to perform a computationally expensive offline stage that is retrieving this B matrix, and then in the online stage you are very quickly obtain new solutions with unseen parameters by predicting these reduced coefficients. And so here again we decided to split a little bit with using all the snapshots or using snapshots coming from the low Reynolds regime and only the snapshots coming from the high Reynolds regime. On POD. And because for turbulent flows, a classic alerting approach is not really well suited. So far, we have decided to work with POD neural networks as a reduced model, where the idea is our POD neural network is given a new parameter, is predicting the reduced coefficients that are used then to generate the approximation of your full order simulation by multiplying by the B matrix obtained from POD. So the idea is you obtain these from the snapshots, these coefficients by projection of the full order simulations, and you train the neural network to copy these projected coefficients. And again, we investigated the possibility of splitting the training into two distinct Reynolds regimes, and we tested our framework on unseen Reynolds numbers. And to give you some insights on the obtained POD neural network, again, it's a really very simple neural network with only 4 hidden layers, 50 nodes per layer, L2 regularization. And we decided to, for each configuration, train 15 neural networks with distinct starting weights and choose the best one in terms of testing error. And just to show you what we obtained, here I'm showing the L2 error on the prediction of the velocity field with respect to the Reynolds numbers. And what we obtain, again, is that if you train a unique POD neural network using all the snapshots, you obtain errors that are, of course, bigger than the errors you obtain by training two distinct POD neural networks, each one focusing on a distinct regime. As a final remark, you can see some sort of discontinuity of the error across the threshold value Reynolds equal to 2000, but it makes sense because the coming full order simulations obtained from the NUTI vector basis neural network were discontinued by themselves because they use two distinct models, one for one region, one from the other. So the snapshots have already themselves some discontinuity across these regions. And with that, I finished, and so thanks for the attention.
Thank you very much for your nice talk. Very fascinating. I think.
Yeah. Yes. Okay. Maybe. Yeah. In general, yes, but not so far. The idea is usually the idea of enforcing physical properties is good when you're trying to extrapolating, because you're enforcing physical properties that otherwise classic machine learning algorithm do not know, so they are not even trying to satisfy um, these properties. And it's not really, in general literature, in this field of literature, we observe that these models are good when you're trying to do interpolation or very small extrapolation, otherwise you obtain shape case with Reynolds number 10 to the 5, just to see what what was able to get. And surprisingly, if I looked to the contour lines, the velocity field, they were almost okay. The problem was the order of magnitude. It was like 3 or 4 times higher than what was correct. So probably you obtain something that is maybe physically with a little bit of sense, but because you are extrapolating too much, you obtain noise, basically.
You think this is the case both for, for instance, the physical parameters, for instance, Reynolds, and also for geometrical parameters?
It really depends. For example, I'm quite sure that if you take this alpha is the steepness, if you take alpha, for example, 3 or 5, what you obtain is hills that are not steep, the opposite of steep. But this changing is so low and smooth that in this case, I would guess the results would be okay. But if you take alpha 0.3, for example, that is very far, very close to the 0.4 extreme value that I used. But here the changing is so fast that you don't obtain, you obtain something that is that has no sense. So it's not really. It's about how the physical parameter affects how the parameter affects the physical behavior. So it really depends. Yeah.
Thanks.
But in general, no, they are not good to circulation. So far.
Any other question? Okay. I have a question.
What?
The first question. The decomposition is used for the Reynolds stress, not for the divergence.
Yeah, the idea.
So how can you justify your?
Basically, the classic approach was this paper by Pope in 1975 that was taking the anisotropic tensor that is the this vector here.
Yes.
To be honest, set dimensionless by dividing by 2 times k, and in this assumption, it states that B is a function only of, by taking my notation, S and W.
Okay.
And starting by this, he uses these representation theorems and obtain this linear combination that is an equality between tensors, in this case, not vectors like mine, with I don't remember how many tensor bases. I took this relation and I compute by myself the divergence. So I take his equality, I took the divergence, And by performing the computations, I could not obtain already this type of equality because you have some gradients of the coefficients that are not scalars. But by looking at the results, I said, okay, now I see that I see S as W, but also see the divergence of S. I also see the gradient of K. And so let's start from the beginning and let's make this assumption. Okay. So it's an assumption I obtained by looking at the results of making a similar assumption, but on the deviatory part of the Reynolds Stress Tensor. Okay, there's some error. It's an assumption I made, and by performing this assumption, usually depends on you can think of depending on these two tensors, but it's not exact. It's an hypothesis. Okay. So that's why I obtained this odd relation. I started by this odd relation.
Okay. And another question regarding your own framework.
Yeah.
Have you trained only on UT and tau your POD?
Yes.
Okay, so it is trained and is trained on.
No, I'm wrong. No, sorry. No, I trained my two models to obtain nu t and t perpendicular. I use this model to generate the high-fidelity simulations with nuancing parameters, and then I perform POD on the velocity field.
Okay.
And so with the POD neural network, I only predict the velocity field. I don't even predict the pressure field because in this square duct flow, the pressure is basically linearly increasing to impose the pressure gradient to push the flow.
Yes. Okay.
Yeah, it's really a two-step process. First of all, I trained this methodology of NUT VBNN to have with DNS data with 13 simulations in order to have a tool that is able to generate hundreds of high-fidelity simulations to then perform POD on the velocities.
Okay. Any other question? Also from online. Don't be shy.
Be shy.
You're right. Okay, let's thanks again, Davide.
Sorry for the technical issues I had.
They are common.